Assalamu alaikum students. Welcome to a new lecture of Engineering Fluid Mechanics 2, and in this lecture we are going to talk about turbines. And so far we were discussing pumps, and today what we are going to do, we are going to discuss the type of turbines, and then we are going to see the torque equations and the power equations that are involved in the working of a turbine. So as we discussed in the case of pumps, the basic purpose of the pump is to increase the pressure. So in turbines, that pressure decreases when the fluid passes through the rotor. So let's look at the type of the turbines, and let's see that how that decrease in pressure occurs across these different type of turbines. And what we are going to do, we are going to discuss these two types of turbines. One is the Pelton wheel, and the other is the that is a reaction turbine. So this is also known as the impulse turbine, and this is the reaction turbine. So the difference between these two turbines is that in impulse turbine, the pressure drops occur inside this nozzle, as you can see, and as the pressure drops occur, the fluid velocity is increased, and this accelerated fluid strike the buckets on this rotor, and the rotor rotates, and then we utilize this rotation energy, which is also known as the torque of this rotor. Then in case of the reaction turbine, what happens that the rotor of the reaction turbines is immersed in the fluid, but the geometry of these rotors is as such that the fluid passes through the guide vanes into the rotor vanes, and the pressure drop occurs inside the rotor vanes, and this is why it is also known as the reaction turbine, that the rotor profile is designed as such that the fluid pressure drop occurs inside these rotors, and the pressure drop is converted into velocity increase. So this is how we utilize the fluid energy by moving, rotating a rotor, and with the help of the impulse or the reaction turbine. So first of all, what we are going to do, we are going to discuss the impulse turbine, which is a Pelton wheel turbine, also known as the Pelton wheel turbine. And here we have two components that we are going to consider. One is the tangential and the other is radial. And what we are going to do, we are going to take the nozzle, and here the water that is leaving the nozzle strikes the turbine rotor right here. So this fluid will have an absolute velocity both as it exits the nozzle and when it strikes the rotor blade and then exits the rotor, and then this blade will have a velocity as well, which is known as u. So the terminologies that we used when we were talking about pumps will remain as such when we talk about the velocities that are involved in the case of the turbines. So this is the equation that we are going to use. This is that the absolute velocity is equal to the relative velocity plus the blade velocity. This is the equation that we used previously, and now what we are going to do, we are going to see our vector triangle vectors for our velocity at the inlet and the outlet. And here we have the blade cross section, and as you can see, the velocities at the inlet have an equation. This equation, you can see that velocity v1 have a tangential component, that is v theta 1, and they will both be equal to w1 plus u. This is your equation 12.48, as you can see. And then we will have exit velocity conditions, and both w1, the relative velocity at the inlet, will be equal to the relative velocity at the exit, because relative velocity is the one that is being observed by someone that is placed on this blade. So, or you can say that the reference for the relative velocity is moving with respect to the blade. So at the inlet and the outlet, the relative velocity will be the same. And now let's have a look at the velocity vectors at the inlet and the outlet for this specific impulse turbine. So these are the velocity vectors for our inlet, and as you can see, the velocity v1 have only tangential component, so the other velocities that are involved will be equal to the sum of this uh, absolute velocity, that is v1 is equal to u plus w1. This is what this diagram is representing, as you can see from the magnitude of v1 is equal to u plus w1. But when this fluid strikes this rotor, its direction will change. The tangential component of the tangential velocity will be tangent to the blade profile, so it will come out to be drawn like this in this direction. The blade velocity will be in the same direction as it was at the inlet, and then we will have the absolute velocity, and as now you can see at the outlet, the absolute velocity will both have an tangential and radial component. So this will be the triangle, velocity triangle at the outlet, and the angle that this relative velocity makes with this axis is known as beta, and this is our inlet and exit velocity triangles for a Pelton wheel turbine. So now let's use these velocity triangles and derive our equations that are related to our torque and power. So again, we are going to use this diagram, figure 12.27, and at the left hand side you can see the vector conditions of velocity at the inlet, and then the velocity triangle at the outlet. So we can also write an equation by using for this triangle. We wrote an equation for this condition, and that was v1, which was also equal to b theta 1 is equal to u plus w1. So this was our condition at the inlet, and at the outlet we have v theta 2. This is this component right here. This component of the absolute velocity at the exit is v theta 2, and v theta 2 here will be equal to the blade velocity at the exit, and the tangential component of this relative velocity, that will be plus w2 cos beta. This will be the tangential component of this relative velocity. So this will be our equation 12.49, and now combining these two equations 12.48, 12.49, we can actually write an equation in terms of the change in the tangential component of the absolute velocity, and this will come out to be like this, and then we can utilize this equation and then derive our equation in terms of torque and power that is involved in this whole scenario by using our previous equations 12.2 and equation 12.4. This is our equation 12.2 that we used previously. So you can see that we can write this equation in terms of v theta 2 minus v theta 1, and then putting the values of this equation 12.50 right here, we can actually get the shaft torque that is involved in the case of a turbine. Then we have also we can also utilize equation 12.4 and then write the power that is involved in terms of a turbine, and write an equation for it as well by using the 12.49 equation, the equation 12.4. So we can also have an equation for our shaft power, and these results are plotted in figure 12.28 along with typical experimental results. So one is the data that we get from these equations, and one is the experimental data that we got, and we will plot a figure graph between the torque, the power involved, and the blade velocity. So now let's have a look at that figure, and then we can have some interesting scenarios. So this is that figure 12.28, and as you can see, the blade velocity, the shaft torque, and the shaft power is plotted for different conditions, and the solid black lines are called these are the lines that we get from the equation, the actual torque, the theoretical torque, and the theoretical power that is involved, and then we have these bars in which we get the experimentally shown torque, actual torque, and the actual power. So here we have different scenarios at zero speed. At zero blade speed, you can see that the shaft torque is maximum. So what does that mean? This means that when the reaction to rotation is maximum. For example, we talked about the what is the difference between moment and torque. We talked about it quite often. So now it is becoming clear and clear that moment is a thing that is applied, that is the action, and torque is something that we get in reaction. So when the shaft reaction is at its maximum, when the shaft torque is at its maximum, it means that the blade is stationary. So when the shaft torque starts to decrease along this line, as you can see, as it starts to decrease, the power that is being transferred to the shaft will increase. And as you can see, the shaft power is maximum at this point when U is equal to 0.5 V1. So here at this condition, the shaft power will be maximum, and when at this condition right here, when U is equal to V1, then here the torque is 0, but the shaft power is also 0. It means that the rotor is rotating freely. It is a case when the rotor is disengaged from the main shaft, and the whole of the fluid energy is being transferred to a rotor that is moving freely, and it is not transmitting any energy forward. So this is the different torque power values that we get by changing the rotor blade velocity, or you can say that we can get these different line by changing the fluid velocity, because it is also related to the rotor speed. So now several interesting points can be noted from the above results. We can also have an angle beta that is involved in the equations that we saw for the torque and the power. So we can also have different values of beta, and then we can have different results. So first, power is a function of beta. As you can see, power is a function of the angle beta. However, typical beta is equal to 165 degrees rather than the optimum 180 degrees. Results in a relatively small, less than 2% reduction in power. So since 1 minus cos 165 degrees results in 1.996 compared to 1 minus cos 180, that is 2. So the difference is not that much, so it can be neglected. Second, although the torque is maximum and the wheel is stopped, U is 0, so it means the torque is maximum. It means the reaction is maximum. The rotor is not rotating. So there is no power under this condition. To extract power, one needs force and motion. So you have to apply force with the help of the moving fluid that is being accelerated by passing it through a nozzle. And on the other hand, the power output is maximum when the blade velocity is equal to V1 over 2, that is the half of the absolute velocity at the inlet. Then at that moment we have the maximum power output. Then this can be shown in equation 12.51, that is the one that is related to the shaft power. Solving for U, that gives partial differential of the shaft power over the differential of the blade velocity is equal to 0. A bucket speed of 1/2 speed of the fluid coming from the nozzle gives the maximum power. So you can actually put this into the equation that we have for the power, and then derive another term that will give you the maximum power. So the third point is that the maximum speed occurs that when the shaft torque is 0. The maximum speed, if we can look at this graph, can occur at this point. Here it is, the speed is maximum where U is equal to V1. So it will be the maximum speed. So here the shaft torque is 0. That is, the load is completely removed from the turbine, as would happen if the shaft connecting the turbine to the generator were to break and frictional torque was negligible. For this case, U is equal to omega R is equal to V1. So as we already discussed the connection, the shaft connecting the turbine to the generator were to break. It means that the rotor is disengaged from the main shaft, and now the uh, whole of the velocity is converted into the blade velocity. The fluid velocity is converted into the blade velocity, and that scenario is known as freewheeling. And the water simply passes across the rotor without putting any force on the bucket. So these are the main equations and the main terminologies that are involved when we talk about the impulse turbine, and the torque and the power equations that are involved when we talk about the impulse turbine. And these equations, these equations are then plotted on this figure right here, and then we have theoretical power shaft uh, torque and shaft power, and then the actual shaft and actual power and actual torque, and then for different value of u we can see the variation in the shaft torque and the power that is given right here. So now let's have a look at this example, that is example 12.6, and in this example we are going to see the Pelton wheel turbine characteristics. So given is the water to drive a Pelton wheel is supplied through a pipe from a lake as indicated in this figure. You can see the lake right here. The lake have at a certain height of 200 feet. Then a pipe that runs from the lake carries the water, and then that water passes through a nozzle and strikes this Pelton wheel. So the characteristic length of the pipe, the friction factor, the diameter are given. The angle beta of the that is involved in this whole flow between the relative flow velocity and the tangential axis is given, and then the diameter of the rotor is given as 3 feet. So the head loss due to the friction factor in the pipe is important, but minor losses can be neglected. So we are going to include the head losses, the major head losses and the minor head losses will be neglected. So what we have to do, we have to determine the nozzle diameter D1, that will give the maximum power output, determine the maximum power and angular velocity of the rotor at the condition found in part A. So first we are going to find the optimum diameter D1, that will give us the maximum power, and then we are going to find the maximum power and the angular velocity at this for this specific nozzle that is involved in this flow. So let's look at this solution as indicated in equation 12.51, that is the shaft power equation that we just saw in our previous slide. The output power depends on the flow rate, that is m dot over rho, and the jet speed at the nozzle exit V1, both of which depends on the diameter of the nozzle. So both of the flow rate and the the absolute velocity are dependent on the nozzle diameter and the head loss associated with the supply pipe. That is the power that is given is in the form of this equation. The nozzle exit speed V1 can be obtained by applying energy equation 5.85 between point on the lake surface where velocity is 0, pressure is atmospheric and is considered as 0, and the nozzle outlet where the Z1 and the pressure at point 1 is equal to 0. So basically they are talking about these 2 points. One is at the surface of this lake and as indicated 0, and the other is at point 1. So when you apply energy equation on these 2 points, you will end up with this equation number 2, as it is represented right here. So where the head loss, the major head loss is represented with this term right here. We know that from the viscous flow in our pipes, we can also find a term for the velocity that is involved in the head losses, and the speed V of the fluid in the pipe of diameter D is applied by applying the continuity equation on the fluid that runs inside the pipe and at point 1. So we have neglected the minor losses as indicated to us in the statement given. So given the given data, equation 2 becomes when we combine these equations. So basically we put the values in equation 2 of the velocity and the head losses, and then equation 2 becomes like this, and then rearranging this equation for V1 we get velocity the velocity V1 equation in terms of the diameter D1, and D1 is in feet. So by combining equation 1 and 4 and using the flow rate equation, that is Q is equal to A1V1, we actually obtain the power as a function of the diameter and the blade velocity that is involved. So U is in feet per second and the shaft power is in foot pound per second. So these are the results plotted as a function of U for various values of D in figure 12.6b. So for different values of U and different values of D, the shaft power is plotted. So you can see these different lines for diameter 0.239 feet, 200 feet, 0.200 feet, and 0.300 feet. So this is the plot that is made from this equation 5 that is involved in this example. So we know from the previous slides that the shaft power is maximum when the blade velocity is equal to half of the absolute velocity at the inlet. So by putting this condition both in this scenario right here and the equation that we just derived for the this equation, we actually get the shaft power in terms of this equation right here. And by maximum power is possible when the shaft power, we apply the differential of the shaft power with respect to the diameter, so that when we equate this to 0, we actually differentiate this equation. So now this equation will end up to look like this. This is how this equation will look like, that is 304 d1 to the power 4 is equal to 1. So now from this equation, the nozzle, the maximum the diameter for which the power, the nozzle diameter for which the power will be maximum can be calculated. So now we know that D1 is equal to 0.239 feet. So thus the nozzle diameter for maximum power output is 0.239. We can also see that from this figure right here that the power, the maximum power is obtained at this blade speed at diameter 0.239. So this is one we can see from the plot, but we can also find that from the equation for that was given to us for the power output. So what we now need to do, we are to find the corresponding maximum power and the blade velocity that is involved for this diameter of the nozzle. So the corresponding maximum power can be obtained by using this equation, and the power involved will be the by solving this equation, it will come out to be 59 horsepower. And the rotor speed that is involved, the rotor speed at maximum power condition can be obtained from this equation right here. And writing this equation in terms of this, we can actually get our rotor speed in terms of the RPM, that is 295 RPMs. So the explanation is quite simple, because for larger diameter nozzle, the flow rate will be high, but the jet velocity will be low. So it will, because of head losses, it will be smaller. So a smaller diameter nozzle will reduce the flow rate, but will produce a large jet velocity, since the power depends on the product combination of flow rate and jet velocity. Therefore, there is a optimum diameter nozzle that gives us the maximum power. So basically, large diameter nozzle will give you higher flow rates but smaller jet velocity and the higher head losses. And smaller jet velocity, smaller diameters nozzles will give you a low flow rate but a higher jet velocity. So there should be optimum range of D for which we can obtain a maximum power and blade speed. As you can see that this is the optimum point right here. This is the optimum point for a combination of U and the diameter of the nozzle that will give us the maximum power that we can get. So these results can be generalized, that is without regard to the specific parameter values of this problem, by considering equation 1 and 3 given and the condition U is equal to V1 over 2 to obtain this equation, and by then solving this equation by setting this criteria again, it can be shown that the d1 velocity is equal to d over 2 the friction factor L over d n2 power to the 1 by 4th of the root, which gives us the same result that we just saw by solving the example above. So this was the example that was quite straightforward, I guess. And this example was related to the Pelton wheel turbine characteristics, in which we saw the effect of the turbine, the nozzle diameter on the turbine power and the blade speed that is involved.